We do have quite a bit of notes today to make it through. We actually had about 15 minutes left last period, so it wasn't too bad, but I do want to make sure we give ourselves plenty of time to get through the notes with a little bit of extra in case you want to have some quick discussions with your catapult group maybe. That due date is coming up. It's the 22nd is the due date for your build for the launch, and then the 24th is your write-up. A couple other things to keep in mind. You have problem set 204. That is due the 17th, so that's next Wednesday. And then your bump assignment is coming up as well. If you haven't looked at that yet, that was the assignment that is optional. You don't have to do it, but if you do it, you can get up to 2 points added onto your report card grade. So I would encourage you to take a look at that in Schoology if you haven't yet, because those things are coming up. So before we get to today's notes, let's go ahead and look at today's warm-up question. It says, if a ball is thrown 30 meters per second directly upwards at t equals 0 seconds, at what other time will it have an equal speed? We're going to assume gravity here to be 10 meters per second, and then we're going to sketch the VT graph. So if you have an object being thrown up in the air, like this guy in my little animation, and yes, I know those are different numbers. I'm not worried about the numbers. Okay, but if you have an object being thrown up in the air, what we know to be true about any object in free fall, which an object thrown up in the air is in free fall, is that its velocity will change at a rate of 10 meters per second each second in the downward direction. So if it's thrown up at 30, then after 1 second, it should be moving 10 meters per second slower because it's accelerating downward and velocity's up opposite direction. Okay, and so we would expect it to go from 30 to 20 to 10 to 0, and then to -10 to -20 to -30. And so when it has the same speed, would be all the way over here. So after 1 second, it's 20, 2 seconds, 3 seconds is 0, 4 seconds, 5 seconds. So it would take 6 seconds for that ball to have the same speed that it was launched with. Could you solve this with kinematic equations instead? Yes. Okay, but it's easy enough to do whenever you're using factors of 10. Pretty easy to just subtract 10 until we get to -30. That is an equal speed, opposite direction, but equal in speed. Okay, so the answer to the first question would be 6 seconds. The second question said to graph this. If I wanted to graph this, I would need to show a velocity time graph where my velocity starts out at +30 and ends at -30, and obviously has to cross that x-axis. It looks like this. This is what your VT graph will look like for any object in free fall that is thrown upward. Okay, the vertical motion will look like this as it goes, like we just said, from 30 to 20 to 10 to 0 to -10 to -20 to -30, so on and so forth. So again, that's your warm-up. You might want to copy that down as something to refer back to as part of your notes. But we're going to get into some more notes today because we're going to be talking about other types of projectiles. An object thrown straight up in the air or dropped from rest, those are projectiles. But we're going to talk today about horizontally launched projectiles. But before we get to that, we first need to talk a little bit more about vectors and vector addition. So vectors are quantities with magnitude and direction, and we represent vectors with an arrow. We use an arrow to represent vectors because arrows can represent both magnitude and direction. The magnitude, or the number value for your vector quantity, can be represented by the length of the arrow. So we can draw a longer arrow if it's a bigger number, or a shorter arrow if it's a smaller number. We've already talked about this before. Okay, I'm just going to recap it because we need to talk about it a little bit more now that we're dealing with projectiles that are moving in two different directions. So again, the length of the arrow can show the magnitude. The direction, of course, can be represented by which way the arrow is pointing, since we can draw an arrow pointing in any direction that we need. We use vectors for quantities like velocity, acceleration, and displacement in this unit. You've used them the most probably with displacement because you saw them in motion maps, and each of those vectors represented the displacement each second. But today we're going to look at them for velocity and acceleration as well. By the way, if you want to follow along, this is slide 202 in the notes. All right, so here is a sketch of a ball that's been thrown upward, just like the warm-up problem. And it has 3 times labeled on my screen: time of 0, time of 1 second, time of 2 seconds. And it says, assume there's no air resistance and that the ball reaches a max height at 3 seconds. Now, I don't have 3 seconds on my screen, but that's okay. The point is that if it reaches max height at 3 seconds, then at 2 seconds, it's still moving up. That's going to help me to draw my vectors. And this is just like the warm-up problem. If I wanted to draw in a velocity vector, I know that this object, as it rises, is going to slow down. So maybe at 0 seconds, it is 30 meters per second. And then at 1 second, it's 20. And at 2 seconds, it's 10. And at 3 seconds, it would be 0. And so I would need to represent the velocities with arrows that have lengths proportional to the magnitude. So that one's going to be the longest because it's going to be moving fastest. And as it rises, it slows down, and so my arrow needs to be shorter. And as it continues to rise, it slows down, and so my arrow needs to be shorter. But they're all moving up because it hasn't yet reached max height. That's at 3 seconds. And so these could represent my velocity vectors for an object that has been thrown upward. Velocities start out higher and then get slower as it rises. We can also draw acceleration vectors. Now this one's kind of silly to draw because my acceleration is the same the whole time. Acceleration for an object in free fall is due to gravitational field strength. And so my acceleration's -10 the whole time, or 10 down the whole time. It doesn't have to be negative if you want to define down as positive. But I would draw my acceleration vectors in, and they're all going to be the same length. Okay, now I know that I drew them in kind of connected to the other one. You could draw it next to it if you'd prefer. That might actually be better to draw it next to it so that you don't confuse it and think that it's the same type of vector, because they're not. The yellow arrows are velocity vectors. The red ones are acceleration vectors. When we talk about vector addition in a moment, and it will be on the notes on the slide, you can't add two different kinds of vectors together. So if you don't want to draw them connected, then don't do that. But you can still see that all my yellow ones are changing, but my red ones are constant. All right, so you can add two vectors of the same type together. Two different velocities I can add. Two different accelerations I could add. But you can't add two of a different type. I couldn't add the two that I just drew, the yellow with the red. But two vectors of the same type can be added together for a visual representation of a mathematical process. Because obviously we can solve it algebraically, but we can also solve it with vector addition by sketching it out. Here's an example problem. It says, the moving sidewalk at the airport travels 2 meters per second forward. If you walk forward at 3 meters per second while you're on this surface, what is your velocity relative to a stationary observer? We did questions like this in the last unit because this is a relative velocity problem. But it's something you can also solve with vector addition. We can add our velocity vectors together using the head to tail method. My yellow vector that I just added to my screen represents the speed of the moving sidewalk, 2 meters per second. Forward, I'm going to go ahead and say it to the right is forward. And then the pink vector represents the walking speed of the person at 3 meters per second, so it's longer. But they're in the same direction. And they're drawn head to tail. Where the first vector ends, the head of that arrow is touching the tail of the second arrow. That's how you draw them when you're adding them. And so if you wanted to answer the question, what is your velocity relative to a stationary observer, you can do that mathematically by adding the numbers, or you can do it with the vectors by drawing in a resultant vector. The resultant vector here is shown in green. It's always drawn from the start of the first vector to the end of the last vector. So it's just a long green arrow in this case. But this represents the resultant, or the total of those two values, which is exactly what you would do if you solved it mathematically. 2 plus 3, same thing. If you want to, you could actually do all of physics with a ruler and a protractor if you could draw things to scale. You wouldn't have to pull out a calculator. You could measure it. I don't know why you would do that. It takes way longer, but you could. And you could actually solve things by doing vector addition and drawing everything to scale on paper. We did a unit like that once, just for fun. But anyway, this is your resultant vector, and it does represent the sum of these two vectors, 2 plus 3. This would have a length of 5 if I had drawn them to scale. All right, please note that both methods give you the same answer. So whether you're drawing them to scale and measuring them, or whether you are adding those numbers, you're still going to get the same thing, 5 meters per second forward. All right, so now that we've kind of reviewed vectors for a moment, we're going to move on to talking about projectiles. We needed to talk about vectors and vector addition because when we start looking at these projectiles, the ones we're starting to talk about today specifically are projectiles that are launched horizontally, like the one in the center of my screen with the cannon. But when we look at that, there is motion in two different directions, and so we're going to look at adding vectors when you have both horizontal and vertical motion. But before we get there, just as a reminder, the only force acting on a projectile is gravity. Okay, it's an object in free fall. We talked about objects in free fall. The only force acting on an object in free fall is gravity, which means that we know the acceleration of these objects. We know that these objects are accelerating due to gravity, which means they all have an acceleration of 9.8 meters per second toward the ground, or you can round that off to 10 meters per second squared toward the ground. But when we talk about projectiles, they could be like our warm-up question, something thrown vertically, launched vertically. They could be things dropped from rest. They could be launched horizontally, or they could be launched at an angle. And up until this point, we've only dealt with one-dimensional motion, things that were dropped from rest or launched vertically, because they only move in one direction, up or down, or up and down. But now we're going to look at things that also have a horizontal component. Today, specifically, we're going to focus on horizontal launches, which, as I said, is what this is showing here. So projectile motion is a form of motion experienced by an object or particle that is projected near Earth's surface and moves along a curved path under the action of gravity only. So again, only force acting on them is gravity. Thus, we will be using two-dimensional vector addition as we analyze the simultaneous horizontal and vertical motion of the object at the same point. So when we look at the path that these objects follow, we're going to look at how the vector addition is what produces that curve that we see. Okay, so again, projectiles often have motion in both horizontal and vertical directions at the same time. Pick a point. I'm going to choose this one. And we can represent the velocity of that ball in the horizontal and vertical direction. I know that ball is moving both forward and down. And so whenever I draw my vectors, they would look something like this. I would have a horizontal velocity vector, which is in yellow here, and I have a vertical velocity vector, which is in pink. And those two things represent the motion of this ball. It's moving both forward and down. But if I wanted to figure out exactly how fast it was moving, I would need to know how much forward velocity it has, how much downward velocity it has, and then I would need to add them together, which we do, again, by vector addition. But I can't add them like this. Remember, I said a minute ago on that slide that vectors have to be added head to tail. Okay, so that's what we're going to do. Add the vectors head to tail to find the resultant. So I could draw it like that. And it doesn't matter if you draw the pink one and then the yellow one, or the yellow one and then the pink one. If I drew yellow first and then pink, I would just be doing the other half of this square. Okay, but here I have my vertical drawn first and then my horizontal, and that's fine. Your resultant would be represented by this white vector. So if I wanted to answer the question, how fast is the ball moving at this point, the answer would be that white vector. I would need to know how much horizontal, how much vertical, and then I could solve for the total. Guys, how would I solve for that white vector? Pythagorean theorem, yeah. A squared plus b squared equals c squared. So there will be some geometry in this unit. And maybe some trig if we need to put an angle in there. Okay, and solve for that. But yes, you can solve for that resultant using Pythagorean theorem. So here's an example. I gave you a really easy one. It says, let's assume that the x velocity is 4, the y velocity is 3. What is my total resultant velocity? Again, I gave you one you probably don't even need to do the math for, but we're going to anyway. A squared plus b squared equals c squared. 3 squared plus 4 squared equals my total velocity squared. 3 squared is 9, 4 squared is 16, 9 plus 16 is 25. Okay, and that's v squared, so if I want v, take the square root, and this is a 3, 4, 5 right triangle, which is why I said you probably didn't even need to show your work for it. But that would be your total velocity at that point. So if you were able to figure out what your vertical and horizontal components were, you could solve for the resultant using Pythagorean theorem, which you can see that you have to use vector addition for. You have to use the Pythagorean theorem because of the way the vectors add. All right, So let's talk about some vocabulary terms that you need to know when we are talking about projectiles. And the first is trajectory. The trajectory is the path taken by a projectile. If we focus just on projectiles launched forward, the path of that projectile is parabolic or curved. So if you look here, you have a curve to the path, and it's because of what we just looked at. It's because of the way the velocities add together, and it's because of the way that the motion of this projectile happens. There is acceleration, but only in one direction, only down. And so it causes that line to curve downward as the vertical component gets longer and longer. The resultant gets steeper and steeper. So anyway, the resultant motion is due to the vertical and horizontal motion when taken together. So again, the trajectories, I've outlined both of them in yellow on my screen, but they are parabolic. They're curved in shape. Here's two more terms you need to know as we look at projectiles: height and range. The height of your projectile is going to represent its vertical displacement, and we can find the height at any given point. So I could look for the max height, for example, which in both of these I've just labeled. Okay, so you could solve for max height, but in that case you'd be looking for vertical displacement. Range, on the other hand, is the horizontal displacement of your projectile. So here are the ranges for each of these. It would be basically from the launch position along the ground to the point it lands. Same thing for both, and I've labeled it in both of those. So again, if you see range, it's asking about horizontal displacement. If you see height, it's asking about vertical displacement. So here's a couple other things you need to keep in mind. As I said, today we're going to focus on horizontally launched projectiles. If there is something launched horizontally, it is implied that there is no initial vertical motion. With that cannon right there, with it launching the cannonball forward, it is implied that it's not moving vertically. So its initial vertical velocity will be 0, and that's going to be true for all horizontal launches. The only thing acting on this object is gravity, and so your acceleration will be due to gravity. Again, you can use 9.8 meters per second, or College Board and MyOpenMath actually both use 10. So you're welcome to use 10. It makes the math a lot faster. You probably noticed that in the warm-up. A lot faster if you can just use 10. The direction of the acceleration, again, always toward the ground. So if you call the ground the negative direction, if you call down negative, then you would call this negative 9.8. But you don't have to. You can call downward positive if you want. If that makes your calculations easier, it is up to you. I went ahead and put negative on it because that's the convention, but you don't have to do that. Just be consistent with however you define it. All right, so I'm going to show you this video clip. It's a demonstration that's going to show two objects that are released at the same time. One of them is going to be dropped straight down. The other one is going to be launched forward, a horizontally launched projectile. And I want you to look at the vertical motion and see how they compare. Okay, so he's just going to demonstrate how the apparatus works. So he's going to demonstrate one of the balls falling and then the other launching, and then you're going to see them him do both at the same time. So that's what it looks like when it falls, and then he's going to show you the launch. So now he's going to do both together, and I want you to look at the vertical motion of the two balls whenever they are released at the same time. One of them straight down, the other one launched forward. Okay, so you probably noticed, hopefully you noticed, that they had the exact same vertical motion. They hit the ground at the same time. Okay, and that is something else that you need to keep in mind whenever we're talking about projectiles, is that the vertical motion is going to be the same for all of them. Okay, for something dropped from rest or something launched horizontally, because both of them are accelerating due to gravity, and that acceleration is vertical. So the fact that it's moving horizontally has no effect whatsoever. The horizontal motion has no effect whatsoever on the vertical motion. They're completely separate. And we're going to keep them separate when we do our math as well. Okay, and you'll see that in a minute. But horizontal motion is independent of vertical motion. Vertically, we have acceleration. In the vertical direction, whether the object is launched forward or dropped from rest or thrown, whatever, at an angle, it doesn't matter. The vertical motion will be accelerated motion. You'll have an acceleration of 10 meters per second toward the ground. Horizontally, on the other hand, you're going to have constant motion. If there was no initial horizontal velocity, if it's just dropped straight down, then it's 0 the whole time. If it was launched forward like the ball was in that apparatus, the ball on the right-hand side, let's say it was launched forward at 2 meters per second, well, it's going to be 2 meters per second the entire time because you have constant motion horizontally. There is nothing happening in the horizontal direction that causes acceleration. The only force is gravity, so there's no horizontal force. Thus, your horizontal acceleration will be 0. Whenever I label these, you'll notice it says a sub x. That's because that's acceleration in the x direction. A sub y would be 10, okay, meters per second squared. So you will have to start labeling horizontal and vertical separately, which you're going to see in just a moment. So let's practice diagramming some vectors. If I wanted to show the velocity vectors for this cannonball along its trajectory, I know horizontally that whatever speed it's launched with, that horizontal speed is going to be the same the whole time. So if I want to add in these vectors, they're all the same length. Okay, so all of those have the same length because there's no acceleration horizontally. I have constant velocity in the horizontal direction. But when I look at the vertical direction, my initial vertical velocity here is 0 because this is a horizontal launch. So you'll notice I labeled it V naught Y. That's my initial velocity in the Y direction. So I have 0 initial vertical motion. But it does start to move vertically because it starts to fall. Once it's in free fall, now it's going to be moving down and getting faster and faster as it falls. And so those arrows in the vertical direction get longer and longer. And again, when you look at the vector addition here, that's what produces the curved shape because as that vertical piece gets longer and longer, it causes that resultant to get steeper and steeper, and that's how you get the parabola. Okay, so again, you can see that you have constant motion horizontally and accelerated motion vertically. We could also add in acceleration vectors. So my acceleration is the same the whole time. I'm going to draw these in green, but they're all going to be exactly the same length because my acceleration is due to gravity the whole time and it's downward the whole time. Horizontally, there's nothing for me to draw for acceleration because there is no horizontal acceleration. There's no force, and so there's no acceleration. So I just labeled a sub x equals 0. Again, you should be able to sketch out vectors or choose a question that has them sketched properly if it was multiple choice. Another thing to keep in mind is that mass has no effect on the motion of a projectile. Okay, we saw this in free fall, and the same thing is true here. I showed you this video of this bowling ball and feather being released in this vacuum chamber, and when the air is removed, they move exactly the same way because mass has no effect on the motion of a projectile or the rate at which it falls. Okay, all objects, regardless of mass, accelerate toward the earth at the same rate, unless there's air. I know in the real world, if you did this in this room, that would not happen, but that's only because there's air resistance. For all of our calculations, we have to assume there is no air so that we can use that number and be able to do the math in the first place. Just a heads up, if there are sometimes misconceptions about mass because when we do things in the real world, we do see differences. But we're going to assume no air, and if there is no air, then we're going to see exactly what they saw when they did it in that vacuum chamber. All right, here's that practice calculation I was talking about. I would recommend that you copy it down. We're going to go through the same process in problem solving that we did for our other kinematic calculations. We're going to start by labeling the positive direction. We're going to analyze the portion of motion that we're considering, and then we're going to label all of our kinematic variables. You'll notice that I made a table in order to label my variables because, as I mentioned, now we're going to have two sets of them, vertical and horizontal, and you do need to keep them separate because what's happening vertically is not the same as what's happening horizontally. They're completely independent of each other. Horizontal motion is going to be constant velocity. Vertical motion is going to be acceleration. So make a T-chart or a table like I have to help you label your variables. But before we do that, let's read the question. It says, a car slides off a flat road atop a mountain falling into deep snow. The car lands 43.9 meters below and 87.7 meters beyond the road's edge. How long did it take the car to fall? How fast was the car going when it left the road? And what is the speed of the car right before impact? Okay, so we've got 3 questions to answer. We're going to focus on them one at a time, starting with how long did it take the car to fall. And the first thing I want to do is identify my positive direction. I need to identify which direction is positive vertically and which direction is positive horizontally. And I have done that by adding axis over there to the side and labeling plus sign for up and plus sign for to the right. If you want to label it differently, you can. You can call down positive if you want. All right, so portion of the motion is free fall. I don't care about the car until it leaves the road. I can't do my calculations until it leaves the road. So we're only looking at the point when it leaves the road until just before it hits the ground. All right. So now we're going to fill in our table. You'll notice I already have some things filled in. I went ahead and called the initial horizontal position 0. So I'm going to say that this horizontal position 0 is over here. That way, whenever I talk about my final position, I'll know that it's 87.7 meters away. Vertically, I labeled my final position as 0. So I'm going to say when it lands in the snow below the cliff, that's 0. Okay, and so I can look at the height of the cliff, and I can take that as my initial position vertically. The other things I labeled were my accelerations. Again, you can fill these in every time. My horizontal acceleration will always be 0. My vertical acceleration will always be 10. And because of the way I labeled my positive direction, mine says negative 10. The other thing that's in here is my initial vertical velocity. Because this is a car just sliding off of a road, it's a horizontal launch. It slides off the road and going horizontally. And so the initial vertical velocity will be 0 for every single horizontal launch. All right, with those things in mind, let's now add some more things to the table. I know that the car lands 43.9 meters below where it fell off the road. So because I called the ground 0, I'm going to call this cliff, this mountain, the height initially, I'm going to label as 43.9. So I filled that into my table. The other thing I see is 87.7 meters. That's going to be my final horizontal position. Because I called the edge of the cliff an initial position of 0, it's going to land 87.7 meters away. That's going to be my final horizontal position. And those are the only 2 numbers that I see in the question. Okay, the rest of them I had to fill in and on my own, and you'll have to do the same thing when you read these. You can fill in, define where your reference point is. So fill in where 0, 0 is going to be. You can do that. Okay, and then you can fill in your accelerations, and then you should have some information about an initial velocity or something else that you can fill in. In this case, I had to assume my initial velocity to be 0 because it's a horizontal launch. All right, so again, first things first, how long did it take the car to fall? That means I need to find time. I'm going to be solving for t. Now, one thing you have to keep in mind when you do these types of calculations is you are only going to be allowed to use numbers from one side of this table. I'm either going to have to use horizontal data to solve for time, or I'm going to have to use vertical data to solve for time, but I'm not going to be able to pick from both sides, so don't do it. Okay, I actually don't have enough information to use the horizontal side. If you look at it, it doesn't really tell me much. It tells me the displacement, and then it says it's not accelerating, and that's not enough information. So we're going to have to start with the vertical side. Because on the vertical side, I know initial position, final position, initial velocity, and acceleration. And if I look at my kinematic equations, I can actually solve for time using that second one, because it has the variables that I know. So we're going to use that. X equals x naught plus v naught t plus 1/2 at squared. I went ahead and put it up here at the top. Again, we're looking to solve for time, so I do want to rearrange this equation and simplify it as much as I can. First thing I can do is, because my initial velocity is 0, again vertically right here, I can cross out that term because 0 times anything will be 0. All right, so that one's going to go away. That's going to make it a little bit easier to look at. X equals x naught plus 1/2 at squared. Again, I want to solve for time, so I need to get the t by itself. I'm going to start by subtracting x naught from both sides. Now I have change in position, or x minus x naught, equals 1/2 at squared. And again, I want to get t by itself, so I need to move that half a to the other side. So I can divide both sides by half a, or I can multiply by 2 and divide by a, same thing. Okay, I divided them both by half a, which ends up being 2 times x minus x naught over a, if you'd rather write it like that. Okay, which is what I did here. The other thing is that's equal to t squared. So I need to take the square root. So if I want to get t will be equal to the square root of 2 times x minus x naught over a. Again, you should be able to do that algebra. That's why we started the year with algebra like that. That is now something you can substitute into. Could you have substituted in all the way up here? Yes. However, again, College Board likes to ask you questions where they say, derive the equation for the time the time the car is in the air in terms of position and acceleration. And guess what? Now your answer is that. Okay, so you do need to practice rearranging those equations with the variables in them. But for time, whenever you're on a test, I would probably plug the numbers in first, unless you're doing a derivation. All right, so now we're going to substitute into this equation. When I do that, it looks like this. 2 times 0 minus 43.9 over negative 10. 2 times negative 43.9 is negative 87.8 divided by negative 10 becomes 8.78. And again, all of that is under the square root, so I need to take the square root of it. Square root of 8.78 is 2.96 seconds. So I have just found the time it took the car to fall. Now, even though I used vertical data for this, the time isn't vertical. Time doesn't have a direction. So we're just going to put the time in on both sides of the table. Okay, time is the only factor that can go in on both sides of the table like that, because it's just time. There's no vertical and horizontal time. So you'll notice I've added it to my table because I might need it for my next calculation, and not might, I will. Okay, and so I have 2.96 seconds. All right, so we've answered how long it takes the car to fall. Part B, how fast is the car going when it left the road? Again, the car left the road horizontally. So I need to look at the horizontal side of my table. Okay, and I'm going to be looking for the initial horizontal velocity. Please only use the horizontal side of your table. You'll notice I just completely took the other one off the screen so that we don't even think about it. So I'm looking to solve for V naught. I have x naught, x, a, and t. If I look at my equations there, the only one I can use to do this in a single step is that one. X equals x naught plus v naught t plus 1/2 at squared. It's the same equation I just used, but now I'm using the other side of the table for my data. All right, so if I plug into this equation, again, first I need to get it set up to solve for v naught. So let's rearrange it first and simplify if we can. That first things first, that 1/2 at squared is going to go away because my a is 0. And anytime you multiply by 0, you're going to have 0 for that factor. So when I start simplifying it, I'm going to cross that off, and now this is a little easier to look at and a little easier to work with. So again, we're trying to get v naught by itself. First things first, subtract x naught from both sides. That gives me x minus x naught, that's displacement, equals v naught times t. And I want, again, v naught by itself, so divide both sides by t. And this equation should look familiar, guys. This is velocity is displacement over time. Okay, I probably didn't have to derive that equation, but we just did. Okay, and you could too. If you have constant velocity, you can use that equation. Okay, so velocity is change in position over time for your anything with constant velocity, which horizontal motion is. All right, so now we can substitute into this equation. So let's go ahead and do that. X minus x naught is 87.7 minus 0. So 87.7 divided by 2.96 gives me an initial velocity of 29.63 meters per second. And I can now add that to my table. And I'm also going to add it in for the final velocity. Because it's no acceleration, my final and initial velocities will be the same for my horizontal motion. And guys, that's true every single time. Whatever your initial is, your final is the same because it's horizontal motion and there's no acceleration horizontally. Okay, so on the horizontal side, you'll look for that. All right, so we have now answered how fast the car was going when it left the road. The last question we're going to answer, what is the speed of the car right before impact? Well, I know how fast it's going horizontally when it impacts. but I don't know how fast it's going vertically when it impacts. And the question isn't asking for horizontal or vertical, it's asking for the total. It just says what's the speed. And it's going both, it's going diagonally when it hits the ground. So I need to find my final vertical velocity, and then I need to find the total resultant velocity. Even though it doesn't say, if it doesn't specify what's the horizontal speed or what's the vertical speed, then they mean the resultant. All right, so with that in mind, we're going to solve for the final vertical velocity. It's the only thing that I don't know yet, and I need to find it to answer this question. Again, looking at my equations, you have some options in terms of which one you're going to use, but the first one's the easiest. It's easier than doing the third one because I don't have to mess with square rooting anything. Okay, so V equals V naught plus A times T. It's already set up to solve for V, so I'm just going to substitute in 0 plus negative 10 times 2.96, which is just negative 29.6 meters per second. So now I know the final vertical velocity, and I've added it to my table. But that is not the speed right before impact. That is just the vertical speed at impact. So if you want to answer the question that's being asked, I need that number, but that's not my answer. My answer is the resultant that I get when I add the horizontal and vertical together. And when I add them together, I don't mean just add the numbers, I mean add the vectors. Because one of those vectors is horizontal and one of them is vertical, when we add them, we're doing Pythagorean theorem. Okay, a squared plus b squared equals c squared. So that's going to be this. 29.63 squared plus 29.6 squared equals c squared. 1,754.0969 is c squared, which means c is 41.88 meters per second. It just asks for what the speed is, so I don't care about the direction. That's my answer. If it had said what is the velocity just before impact, I would need to calculate the angle as well. And I would have to use trig, and I'd be looking for the angle it hits the ground at, just as a heads up. That is possible that we ask you that. And are there any questions about this? Yes.
You knew that we were talking about, like, we had to find
the resultant?
Yeah, because it just said the speed of the car, didn't say like horizontal or vertical.
Right, because it just says what's the speed of the car right before impact, it wants the total speed. All right. Okay, guys, that is it for today's notes. What I'd recommend you do right now is discuss your catapult project with your group, and if anybody doesn't have a group, I need you to come talk to me so I can get that fixed for you right now. Because your build is due on the 22nd, and that's going to be here faster than you think. 204 problem sets are due the 17th. If you haven't already done so, there is a paper copy of the workbook pages up there. Please grab that. The rest of it's in my open math. And then if you haven't glanced at that bump assignment yet, that would be a great idea to do so right now if you're considering doing that. Go ahead and get to work. You guys have about 15 minutes. If you have questions, let me know. But these are things that you can be working on right now.